Hello, I welcome you all in this course on refrigeration and air conditioning. Today we will continue our discussions on aircraft refrigeration cycles. In this lecture we will cover the simple air refrigeration cycle with evaporative cooling, bootstrap air refrigeration cycle with evaporative cooling, air refrigeration cycle with regeneration, reduced ambient air refrigeration cycle, DART, irreversibilities in air refrigeration cycle. Now, we will start with simple air refrigeration cycle with evaporative cooler. In previous lecture, we have already discussed the simple air refrigeration cycle that is 0, 1, then compression 2, then cooling, constant pressure cooling, this is P1, this is P2, constant pressure cooling, and then expansion in expansion turbine. Now, in this evaporative cooler, in this cycle, evaporative cooler is introduced just before the expansion turbine. This evaporative cooler further cools down the temperature of air before the expansion and expansion turbine. By providing evaporative cooler, the gas is further cooled up to the state 5 and then expansion takes place and we get state 6, this is state 4. So, you can see from here the temperature at state 6 is less than the temperature at state 4. We get, in this case, we get a cooler air entering the passenger cabin, or we can say the same amount of circulated air can take more refrigerating load. Same arrangement is made in the bootstrap of a cycle. In bootstrap cycle, you know, there is a two-time compression, first, then second compression 3, and then cooling 4, and 4 to 5 expansion takes place. But in this case, the gas will get further cooled to 6 and expansion will take place up to 7. Now, evaporative cooler, they provide additional cooling to the gas which is entering the expander, by virtue of which we get cooler air at the exit of the expander or the turbine. Now, evaporative cooling is attained either with the help of some refrigerant or liquid nitrogen, and this evaporative cooling type of arrangement is very useful when the aircraft is moving with a very high velocity or supersonic velocity. Now, we will discuss air refrigeration cycle with regeneration. Now, air refrigeration cycle with regeneration, initially the processes are same. Due to ramming action, the pressure and the temperature of the air is increased starting from state 0 to state 1. After the state 1, the state 2 is attained in a compressor, state 2. The air coming out of the compressor is cooled at a constant pressure. This is a constant pressure line, this is temperature on ordinate, on abscissa there is entropy. So, at constant pressure the cooling of air takes place and state 3 is attained. After the state 3, there is a heat exchanger. This heat exchanger, as shown in the figure, takes air after the expansion of turbine. So, part of the air after the expansion of turbine, it is recirculated through this heat exchanger, so that the temperature of air is further cooled to state 4. So, due to this heat exchanger, instead of attaining this temperature 1, 2, 3, the gas is further or air is further cooled up to temperature 4 and further expansion takes place. In this case also we get cooler air at the exit of the turbine. Now, here the point is, suppose 1 kg per second is the gas air circulation rate, part of this air, maybe 5% or 10%, will be tapped at state 5, and this trapped air will be sent to the heat exchanger, and in the heat exchanger this low temperature air will take heat from the air which is entering the turbine and it will further cool it. So, this type of arrangement is also possible in air refrigeration cycles. Now, the last one is a reduced ambient air refrigeration cycle. In a reduced ambient air refrigeration cycle, before entering the compressor, the air is trapped and it is passed through a turbine which produces work and the pressure of air is reduced because it is an adiabatic process, reversible adiabatic process. So, if you look at the state 5, state 5 say at state 1 the air may be available at let us say minus 20 degree centigrade, but after the expansion the temperature of air will further reduce. So, this low temperature air will now be used for cooling the gas coming from the compressor. So, definitely this will also improve the performance of the cycle, and whatever work is produced in this auxiliary turbine during process 1 to 5, this work is added to the fan work because in this cycle a fan is run by the auxiliary turbine. This is expansion turbine. The fan is run by the expansion turbine and the air circulated by this fan is used to take away heat in the cooling heat exchanger. Now, these are the 6 type of cycles which are used for air refrigeration systems. Now, if we compare these cycles, if we compare these cycles with each other, I have taken on the x axis Mach number, on y axis it is dart is dry air rated temperature. Dry air rated temperature is the temperature of air at the exit of expansion turbine or temperature at state here in the state 5 or state 6. So, dart, if you look at the dart and with the help of dart if we try to compare the performance of all these cycles, if you look at the simple air refrigeration cycle, dart keep on increasing. If we increase the velocity of the aircraft, the dart keep on increasing. So, this cycle cannot be used for very high velocity aircraft. And if we look at the bootstrap is much better than the simple refrigeration cycle, and we can go for the bootstrap even the supersonic aircraft. It is because if let us say Mach number is 1.2, the value of dart is minus 40 in bootstrap cycle, and further we can go up to 1.2, 1.4 or up to 1.6, but for further increasing the Mach number, the regeneration type of cycle is recommended for high Mach numbers. If you look at 1.6 Mach number, here you can see that the value of dart is close to 0, but value of dart for bootstrap is on positive side of temperature, positive temperature, some 10 or 20 degree centigrade temperature. Now, for very high velocity aircrafts, we can go for reduced ambient type of cooling system. You can see the reduced ambient type of cooling system is very stable up to let us say 2 or 2.2 Mach. We can comfortably go with this system, but the aircraft has to fly on very high speed, let us say 2 Mach or 2.5 Mach. In that case, the best one is bootstrap with evaporative cooling. So, bootstrap air refrigeration cycle in combination to evaporative cooling is best suited for high velocity aircrafts. Now, irreversibilities in air refrigeration system, because till now we have considered all processes as reversible process, but in actual practice none of the process is reversible process, almost all the processes are irreversible process. Let us start with the state 0, when air is coming with a very high velocity towards the aircraft, state 0, and it get compressed to state 1 during ramming action. If we apply the first law for open system, then H1 is equal to HO plus CO square by 2. H1 minus HO is equal to CO square by 2. Now, as we know, the change in enthalpy in sensible heating or sensible cooling is because here it is a adiabatic compression, and we have already derived in adiabatic compression the change in enthalpy is Cp T1 minus T2, T1 minus TO, Cp dt is equal to CO square by 2. Now, T1 minus TO is equal to CO square by 2 Cp, or we can write as CO square divided by 2 gamma over gamma minus 1 into R, because Cp is equal to gamma over gamma minus 1 into R. Now, further, if we divide the entire equation by TO, so T1 by TO shall be equal to 1 plus CO square 2 gamma R TO divided by gamma minus 1, right, and then TO by T1 is equal to 1 plus gamma minus 1 by 2 CO square, and this gamma RT can always be taken as sonic velocity at this particular temperature, and this ratio will give you TO by T1, sorry, T1 by TO. This is T1 by TO. So, here also it is T1 by TO is equal to 1 plus gamma minus 1 by 2 m square. From this equation, if we know the value of Mach number, suppose the aircraft is moving with m is equal to 1, let us say it is sonic aircraft, m is equal to 1. So, immediately we can find that T1 by TO is going to be equal to 1 plus gamma minus 1 by 2, or it is going to be gamma plus 1 by 2. But in actual practice, this process does not take place. Instead of pressure rising up to P1, from PO to P1, the pressure rises up to P1 dash only. So, entire stagnation pressure is not attained, but part of the stagnation pressure is attained, but the temperature at this point, this is 0.1. So, instead of getting 0.1 in the process, in a irreversible process, we get 0.1 dash. Now, temperature of 0.1 dash is equal to T1. So, T1 dash is equal to T1, but the pressure of at this state is less than the pressure of at the state 1, and there is a pressure recovery factor PRF. Pressure recovery factor is P1 dash minus PO divided by P1 minus PO. After attaining state 1 dash, the air goes to the compressor. Now, inside the compressor, ideally there is an isentropic process or reversible adiabatic process. There is no heat transfer during this process, and we get state 2. But in actual practice, it is a irreversible process. Due to irreversibilities, it is no longer a vertical line, or entropy does not remain constant. There is a change in the entropy, and we get state 2 dash. If you look at here, the temperature at state 2 dash is greater than temperature at state 2. This is due to irreversibility in the process. And there is a term which is known as polytropic efficiency. So, polytropic efficiency of the compressor can be expressed as T2 minus T1 divided by T2 dash minus T1. definitely in this process, process 1 to 2, energy consumption is less in comparison to process 1 dash to 2. In process 1 dash to 2, the energy consumption is less in comparison to the actual process, that is 1 dash to 2 dash. This polytropic efficiency for a rotary compressor is approximately of the order of 90%. It varies in fact, but normally it is between 85 to 90%. After the attaining process 2 dash, cooling of air takes place. It is supposed to be at a constant pressure P2, but in actual practice there is always a pressure drop. So, instead of P2 there is a pressure P2 dash, P2 dash, and temperature, let us say temperature 3 is attained. This is state 3. So, state 3 is attained at a constant, it is supposed to be a constant pressure process, but since the gas passes through the heat exchanger and it passes through the pipes also, there is certain pressure drop during this process. So, instead of getting temperature state 3 at pressure 2, we attain it at a pressure 2 dash, which is slightly less than the pressure 2. After attaining the state 3, the expansion takes place. I am taking the simple cycle, expansion takes place, and during this expansion also, the expansion takes place inside a turbine. So, this is an ideal process, but in actual practice it is no longer a vertical line, it is no longer a constant entropy process. Again, during this process the entropy increases. The increase in entropy during this process due to irreversibilities present during this process, and instead of getting state 4 we get state 4 dash, and temperature of state 4 dash is higher than the temperature of state 4, or after expansion the temperature is higher in case of irreversible process in comparison to the reversible expansion. And here also the efficiency of the turbine, polytropic efficiency of the turbine can be expressed as T4 dash minus T3 divided by T4 minus T3. So, it is, if you look at these two equations, this is ideal temperature drop in compressor, ideal temperature rise, actual temperature rise. This is ideal temperature rise, actual temperature rise. Ratio of these two will give the polytropic efficiency of the compressor. In case of turbine, it is reverse. Actual temperature drop divided by ideal temperature drop. So, this is this expression is for the polytropic efficiency of the turbine. If you are using bootstrap cycle, in case of bootstrap cycle, again some pressure drop will be here, and again during the compression process there will be irreversibilities or there will be rise in entropy. So, in bootstrap cycle also again the same type of phenomena takes place. So, in a bootstrap cycle again the pressure this compression in the secondary compressor, again it is not a reversible process, and change in entropy takes place. That is why temperature at this state, maybe let us say this state is 5, T5 and T5 dash. So, T5 dash is greater than T5, and in this case also the efficiency of turbine is in the range of 85 to 90%. So, while dealing with the real life problems, we have to take into the consideration with the efficiency of all the components in an air refrigeration system. Normally the efficiency of the rotary machines, because in the air refrigeration system rotary machines are used. So, normally the efficiencies, polytropic efficiencies of the rotary machines are higher than the efficiency of reciprocating machines. For example, if I take reciprocating compressor. So, for a reciprocating compressor, the 80% efficiency is very high efficiency. Normally, it lies between 70% and 80%. The reason being that if, let us take example of axial flow turbine or axial flow compressor. In axial flow compressor, there is no change in the direction of the fluid. Fluid straight away passes through the compressor. Since there is no change in the direction of the fluid flow, that is why the losses are minimum. So, highest efficiency is attained with the axial flow compressors. Now, if we replace axial flow compressor, and it is always close to 90% or greater than 90%, if we replace the axial flow compressor with a centrifugal compressor. In a centrifugal compressor, the direction of the flow of the fluid is like this. There is an axial entry of the fluid in the centrifugal compressor and there is radial exit. And change in the direction of the fluid is approximately 90 degree, That is why in centrifugal compressors, the losses during the flow are more than in the case of axial flow compressors, and efficiency of this compressor is slightly less than the efficiency of an axial flow compressor. And if you go to the reciprocating compressor, the efficiency is minimum. However, in most of the cases in air refrigeration system, axial flow compressors are used because in air refrigeration systems, high bulk of fluid has to be handled. If very high bulk of fluid has to be handled, the axial flow compressors are the best kind of compressors. So, here with this, I end the discussions on the air refrigeration cycles. In the next class, we will try to solve one numerical on air refrigeration cycle.